Okay, so let's get the worksheet out from yesterday. I want to go over a couple of them, but I'm not going to spend a lot of time on this because if you're just not ready to turn it in today, you can turn it in tomorrow. But make sure when I start notes for this new lesson that you put this away and don't work on it during the notes. The people that were here yesterday, we talked about on the front side, remember extreme value theorem, like number 1 and number 3, number 4, extreme value theorem. If you have a closed interval, then you for sure have a max or a min. It might be at those endpoints, but because it's continuous on a closed interval, you do have a max and a min. On an open interval, you might not have both, and we discovered on some of the bottom ones that you don't have any. Like I think on number 5, you should find that there's no extrema because it's an open domain, and if you try to set the derivative equal to 0, you get imaginary numbers. So just have some work to do there on the front. Number 1, number 2, you're supposed to be able to look at the graph. But let's look on the back here. I don't know, probably number 10. That looks terrible, right? Number 9 and number 10, those probably look the worst, right? Number 9 is finding values that make the mean value theorem true. That's not so bad. Number 10, find the derivative at each critical point and determine the local extreme values. Number 10 is kind of very similar to the one that we did on the board yesterday for those people that were in here of you could multiply that out first, or you could do the product rule. So let's look at that one really quick. And notice they tell us here where x is greater than or equal to 0. So they're just giving us a domain on that, telling us that we're only looking at values greater than or equal to 0. So if I'm looking for my critical points, I'm going to find my derivative. And the one we did yesterday, we did, what am I putting 3/2? We did the product rule, right? So we said 2/3 x to the negative 1/3 times x squared minus 9 plus x to the 2/3 times x squared times the derivative there, which would be 2x. And so again, we have options here, but I'm going to stick with the same way we did yesterday, which I think was just the easiest way to do this, of this equals 0. So if I write this, I would get 2 times x squared minus 9 all over 3x to the 1/3, or the cube root of x. And then x to the 2/3 times 2x. Remember, I'm adding those exponents when I multiply. So 3/3 plus 2/3 would give me 2x to the 5/3. Yesterday, we subtracted that part over and just solved it from there. We also could get a common denominator. I'm going to do that just for the whole increasing and decreasing thing that I have to do in a minute. So my common denominator would be 3x to the 1/3. So this part isn't going to change, right? That's going to stay 2x squared minus 18. I'm just going to distribute. But over here, right, that's over 1. So I have to multiply by 3x to the 1/3. And just like the one from the homework, it works out really nice because x to the 5/3 times x to the 1/3, I just add and I get x to the 6/3, which is just x squared. So I think you should get 8x squared minus 18 over 3x to the 1/3 power. So set that equal to 0. The top, right? We just set the top equal to 0. 8x squared minus 18 equals 0. 8x squared equals 18. Look how much algebra we're doing here. What would that be? 9/4. Take the square root, which we would normally say plus or minus, but remember our domain is greater than or equal to 0. So I'm just going to take the positive root, which would be 3/2. Remember that critical points are also where we get 0. And I think if I sorry, where I get 0 in the denominator, which 0 in the denominator would be a problem here. It is part of our domain, 0 is, and if you plug 0 in that problem, I think you just get a value. So I think we do need to check 0 here, but the problem is we can't really see what's happening to the left of 0 because our domain starts at 0. So that's something that we might want to think about. Maybe we want to look at the graph in a second. So when I make my chart here, I'm going to start here at 0 because remember that my domain said greater than or equal to 0. And I'm going to plug in 3/2 and kind of see what's happening here. So I'm plugging into my derivative, which kind of messy, but I think that this was my derivative. So if I pick a number between 0 and 1.5, I'm going to pick 1. And remember, I'm really just kind of looking whether it's positive or negative. And I think on here I would get what? I would get a negative number on the top, but a positive number on the bottom. So I would get negative there. Okay, goodness gracious, I was having an issue. Here's my problem. Hopefully you guys figured this out. This is not my derivative, right? This was my simplified derivative. I was missing this whole part here. Whew, okay, sorry. We're plugging this into my simplified derivative, which should be this part right here. And if I plug 1 in there, then I definitely get a negative number. If I plug a number bigger than 3/2, like let's just say 2, if I plug 2 into this derivative, I'm going to get 4 times 8, which is 32 minus 18, which is positive. The bottom is positive, so I get a positive number, which tells me that my graph is increasing and then decreasing. So that would mean it would look like, well, that's not right. Why do I? Oh, I should not be teaching. Negative does not mean it's increasing, right? Negative means it's decreasing, and this is increasing, which means that it should look like that, like a relative minimum, which if you graphed it, you saw that already. Because 0 is included, if you look at the graph there, right? If you look at the graph, like starting at 0, it kind of goes and it looks like this. Since 0 isn't included endpoint, should we say that 0 is a relative max, meaning that there's not anything else bigger than it? An absolute max. But I think we could say that at 0, whatever we get, we would have a relative max. And then at 3/2, whatever the y value is, we would have a relative min. And then I'm going to leave it for you to find the y value. And remember, to find the y value, you go back to the original equation. Okay? If you have other questions on this or you didn't get it finished, keep it for tomorrow, but go ahead and put it away. And that way we can take a few extra notes. They're pretty short. If you don't have the notes yet, go ahead and pause the video until everyone gets a copy of the notes. Okay, first derivative test. I kind of feel like I've already ruined this for you because we've kind of done it already. But the first derivative test is going to help us find local extrema points. And we're not going to need a graph anymore to find relative max and relative mins, kind of like what we ended for 2 with. And it says, differential calculus is a powerful problem-solving tool precisely because its usefulness for analyzing functions. Especially think before they had graphing calculators, how useful this is. But really, really cool stuff. So really nice for you. I printed these for you so to write them all down. But the first derivative test uses the first derivative to find relative extrema points. So if you have a critical point C for some function, so you set your derivative equal to 0 and you find that it equals some value C, if your derivative changes sign from a positive to a negative at C, so your derivative is positive, which means increasing, and it changes to a negative, which means decreasing, then we know that the function has a local maximum at C. And we can say the same thing, that if your derivative changes sign from a negative to a positive, and we know a negative derivative means your function's decreasing, to a positive derivative, which means it's increasing, then we know decreasing to increasing is going to give us a relative or local minimum value. And we've already seen, what's the third option? Well, what if it doesn't change sign? What if it's positive, positive, or negative, negative on either side of those critical points? Well, that just means that it has no extreme value at C. So critical points are possible local extrema, not guaranteed local extrema. So let's just practice a couple examples, and then tomorrow when I come back, we're going to add on to this and learn some cool stuff about the second derivative and what we can know from graphs just by looking at the second derivative. But today, if you've been doing your homework, today is really not earth-shattering in terms of new calculus knowledge. But it does say use the first derivative test. So you have to know what that means, which just means look at whether it's changing from positive, negative, negative to positive. So find the local extreme values. Step 1, find my derivative. And I would get 3x squared minus 12. So 3x squared minus 12 equals 0. It's not undefined anywhere. You could divide by 3, or you could just add 12, then divide by 3, and we get x equals plus or minus 2. And hopefully the same way you finished 4-2 day 2 notes, and the same thing you did on your worksheet, is you know now that you can just think about from negative 2 to 2 and look and see what's happening with the derivative at those points. And so really want to make sure you're plugging in to the derivative and you're just looking for positives and negatives. So I don't ever actually put the value there, because sometimes people get confused and they want to say that's the y value that goes with it. I just look for positives and negatives. So I'm going to pick negative 3 into my derivative. And if I plugged negative 3 in there, I would get 3 times 9, which is 27, minus 12, which is a positive number, right? So that means this is positive, or the function is increasing less than negative 2. Guess what number I'm going to pick between negative 2 and 2? I'm going to pick 0. And if I plug 0 in there, I can see right away I'm going to get negative 12, and that's negative. And then I'm going to plug 2 in there, and maybe you know already that I'm going to get positive again, because I'm going to get the same thing, 27 minus 12, because it's x squared. So I can see, without ever graphing this, looking at this graph, that, and if you ever forget, just draw the picture, right? It's increasing to decreasing, it's decreasing to increasing. So I can say that there is a relative max, or a local max, at negative 2 something, and when there's a relative or local min at 2 something. And how do I find that something that goes with it? I plug it back into the original function, right? So if I plugged negative 2 into that original function, I would get negative 8 plus 24 minus 5. Is that true? Is that 11? I don't even know at this point in my life. That would be negative 13 plus 24. Yeah, that would be 11. And if I plug positive 2 in, that would be 8 minus 24 minus 5, or 8 minus 29 would be negative 21. I'm not promising my arithmetic is always correct, but that's what we can say using the first derivative test. I'm not promising they're going to be all polynomials, because we want to practice our algebra as we do this as well. We want to not be relying on our calculators. Questions like this would always be on a no calculator part of the test, because remember that you only get a graphing calculator, so they're not going to give you something to look at a graph to find max and mins. It's always going to be without a calculator. Oh, look at this e to the x. Again, you have options. You could distribute or just do the product rule. If it were me, I would just do the product rule because even if I distribute, I'm still going to have to do the product rule. So the derivative of the first is just 2x times the second plus the derivative of e to the x is just e to the x times the first, which means I just get exactly what I started with, right? And so ln and e are going to show up all over the AP exam on the no calculator part because they expect that you can work with e without a calculator. Don't freak out, right? We could factor, we set this equal to 0. I'm going to factor an e to the x out. And if I did that, I would be left with 2x plus x squared minus 3. And remember the lovely 0 product property that we can say we can break that up and either e to the x has to equal 0 or I'm going to change it around, x squared plus 2x minus 3 has to equal 0. So probably you're more comfortable with the quadratic. And we could factor that into 3 times 1 plus 3 minus 1. So we get x equals negative 3 and x equals 1 as critical points. What about e to the x equals 0? If you don't remember the answer to this, you could say, well, ln it, right? That's what you guys always want to do. If you ln both sides, that cancels that out. But what's the ln of 0? Can't do it. If you try it on your calculator, it says domain error. You can't take the ln of 0 or the ln of a negative number. And look back at this. Is there any exponent you could ever pick that would make that go to 0? And hopefully you kind of remember what e to the x looks like, which kind of is like this, right? So it's never going to be equal to 0. So this gives us no critical points. Over here we have 2, so now we can check negative 3 and 1. And remember, we're plugging them into the derivative, which I'm going to plug it into this part of my derivative. Again, don't freak out without a calculator because you think, how can I pick numbers for e? I don't have a calculator. What do you know about e to the x when you plug numbers into it? It's never going to be negative, right? Look at my graph. It's never going to be negative. So when I plug numbers in for e to the x, they're always positive. So it really has nothing to do with the increasing and decreasing. It's always a positive number. So I'm really just looking at these values. So if I pick a number like negative 4, I would get negative 8 plus 16 minus 3 is a positive number because e to the x is also a positive. If I pick something in between negative 3 and 1, let's say 0, I would get 0 plus 0 minus 3 is a negative number. People get really, they want to assume things, and they want to say that for sure after 1 is going to be positive. And I'm not saying it's not going to be, but remember that it doesn't have to be a max or a min. So you always want to check on this. So I'm going to check when I plug in 2, and I would get 4 plus 4 minus 3, which is a positive number. We're going to talk about this more, but I do want to tell you that on the AP exam, if they ask you to justify your answer of how you know there's a relative max or a relative min, this chart right here does not count as a justification. Like you would have to say that there is, let's see, we could say increasing to decreasing, decreasing to increasing. We could say there's a relative max at negative 3 something, and if they ask you to justify your answer, you can't just say, well, look at my sign chart. You have to say, because, we could say g prime of x changes from positive to negative at negative 3. Or another way to say it, I'm not going to write this, but we could say because the function changes from increasing to decreasing at negative 3. So just be aware of that, and we'll talk about that a lot more. And then we could plug negative 3 in there to get the y value, and we could say that there's a relative min at 1 something. And yes, our answers aren't going to be that nice without a calculator. if I plug negative 3 in here, I'm going to get 9 minus 3 times e to the negative 3. I'm going to erase some of this. So I'm going to get g of negative 3 is 6e to the negative 3, or 6 over e cubed. And g of 1 would be 1 minus 3 times e, or just negative 2e. So we could say relative max at negative 3, 6 over e cubed. And we can say relative min at 1, negative 2e. So we're going to see e a lot, so we're going to hopefully get a lot more comfortable with it. I know that's kind of a mess there, but hopefully that makes sense. And today's homework's pretty short. You're just doing 1 through 6. And tomorrow we will turn in the worksheet, and we'll talk about this, and we'll move on. If you have lots of questions left on the worksheet, please come in early so I can help you. Get started on either this or finishing your worksheet. It's not an option just to talk the rest of the hour.